Welcome everyone. I am Dr Ranjodh Rai, and I currently do a bit of R&D consultancy for NeuWave Technologies in Manchester. They do wave data analytics for anyone with any offshore assets. So we mainly focus on offshore renewable energy. And my talk is called "The Role of Mathematics in the Technological Advancement of Offshore Renewable Energy." So before I went into this job, I did a PhD at Manchester Metropolitan University on hydrodynamic modelling of offshore renewable energy, and that essentially got me into this field because when I left university after I'd done my MMath, I didn't really know what I wanted to do, and I sort of stumbled across this PhD, and ever since then I've sort of got an understanding and got an appreciation of the role that mathematics actually plays in solving some of the challenges that we have in the world today. Because I think I've always loved maths, and I think some of the time people don't necessarily have an appreciation for the role it plays in everyone's lives. And technology obviously is an obvious one. So today I sort of want to talk about the role it plays in offshore renewable energy, and hopefully it's not too maths heavy. I more wanted it to be a bit interesting, so I'm not going to go through a lot of equations and stuff, but more of an idea of where it's essential, how it helps to solve challenges, and some of the interesting parts that people don't necessarily think about either. So I hope you all enjoy it. So the first bit, a bit of background. I've got in the top left here a quote from the IPCC, the Intergovernmental Panel on Climate Change, and they made this in 2023. I have all these references on the last slide if anyone wants to have a look themselves, but I've just referenced it here. And they say that more than a century of burning fossil fuels, as well as unequal and unsustainable energy and land use, has led to global warming of 1.1 degrees above pre-industrial levels. And because of that, in 2015, we had the 2015 Paris Agreement, which compelled nations to limit the increase to well below 2 degrees Celsius, whilst also endeavouring to limit the rise to just 1.5 degrees Celsius. And I've put that 1.5 degrees in red because we actually had it reported this year that 2024 and 2023, the rise was at 1.5 degrees. So we're already past that point 10 years on, which shows the scope of the challenge. And given the events of this week as well, I mean, we had the new president of the United States signed an executive order to pull out the 2015 Paris Agreement. So there's a lot of challenges associated with this as well. But this is the whole point of where I think mathematics can play a part to solve all these challenges. So from that we have the need to reach net zero greenhouse gas emissions by 2050. That's the main goal for most countries. And the International Energy Agency in 2022 estimated that approximately 1/3 of carbon dioxide emissions came from electricity generation, and because of that, decarbonising electricity generation is the key objective on the road to net zero. So low carbon and specifically renewable sources of energy have become more prominent around the world, and with the accompanying economic opportunities presented by green industry, it's become a major part of future industrial strategies of different countries. Focusing on the UK today, I mean, the new government wants clean power by 2030, and a lot of our industrial strategy is now based around that. There's loads of different types of renewable energy. So throughout history, we've had renewable energies. The main one has long been hydropower, which has been the most successful. There's the Three Gorges Dam in China, which I think is the largest electrical power station in the world, and has an installed capacity of over 20 gigawatts, which is more than the entire installed capacity of offshore wind in the UK. So it's absolutely massive. But I'm going to focus on the UK primarily in this talk. And for us, the main proven source of renewable energy is the offshore marine environment, primarily being offshore wind, but other ones too. And we're very much a world leader in this. So I've just got this graphic from the National Energy Systems Operator, and we can see that on Sunday, 22nd December 2024, we had a low carbon percentage of electricity generation on that day was 84%, with 64.8 of that being wind, and that is very good. If we reach for our goal to be clean power by 2030. This is obviously a good thing, so that's good. And I think last year in 2024, on average, the amount generated by renewables was just above 37%, and low carbon altogether, if you include nuclear as well, it was over 57%. So we are doing well, but there's obviously a lot more to do as well. And that is exemplified by this graphic. Just 5 days later, on Friday, the 27th of December, we have 34% low carbon, so 9.3% wind. So it wasn't a very windy day. So it just shows the challenge that there still is, given that just 5 days later we have this sort of situation, which isn't very good, obviously. But this just shows the challenge that we have in terms of all the other things that are connected to it in terms of storage and stuff like that as well. So if we double the amount of wind turbines we had on Sunday 22nd, we'd have, say, 120% wind. So we'd have excess. So if we had more storage, we could use that on the day here. So there's a lot of ways to solve this, but hopefully we're on the right track. Types of offshore renewable energy. The main one being bottom fixed offshore wind. So wind turbines are very simple. They capture kinetic energy from the wind and convert it into mechanical energy that drives the generator and produce electricity. So most of the structures that we have in the UK are bottom fixed for water depths of less than 60 meters. And the UK currently has 14.7 gigawatts of installed capacity, with approximately 18 gig under construction or committed. And to reach our 2030 target, we need to be between 43 and 50 gigawatts. So there's still a long way to go. Two different types here. We've got tidal stream and floating offshore wind. So tidal stream, tides are highly predictable. You're never not going to get tides. We're always going to have the moon. We're always going to have the sun. So the potential here is to provide up to 10.5 gigawatts in the UK, which is a decent whack. So, but we currently only have 200 megawatts in the pipeline for 2030. So the technology is still in its infancy, but if the technology becomes cheaper over time, this new technology, we will always have tides, so that will always be an option. The other one is floating offshore wind. So these can be placed. These are not bottom fixed turbines. They have platforms like the little graphic here and can be moored into the seabed and float around. And the advantage of these is they can be placed in water deeper than 60 meters. So you can put them further out to sea where you're more likely to have windier conditions. So because of that, they can have a higher capacity factor. So your capacity factor is the amount of energy that is converted into a useful form as a ratio of the one that isn't. So fixed wind turbines generally have a capacity factor of about 40%. And Hywind Scotland was a prototype wind farm, floating wind farm off the coast of Scotland, the first of its kind in the world. That was operational, I think, about 4 or 5 years ago, and that had capacity factors over 50%. So given that was just a prototype design, and that had a capacity factor of over 10% higher, you can see the potential here for that. And because of that, the Greenvolt wind farm is fully consented and is going to be built off the coast of the east coast of Scotland, somewhere in the Moray Firth, by 2029, and that's going to have a capacity of 500 megawatts. So that's very exciting, and hopefully that will be a more advanced technology than the original Hywind Scotland. So it'll be great to see what the capacity factor of that will be compared to normal fixed turbines. And then we've also got wave and floating solar. So wave energy theoretically has the most potential out of all sources, but it comes with a lot of complex engineering challenges. So ocean waves hold enormous amounts of energy, meaning that the survivability of any wave energy converter structure is immediately challenged. And then that's compounded by the fact you have to actually extract the energy and consequently generate the electricity at a high enough efficiency to make it viable. And the whole thing there is an incredibly challenging endeavor. So a lot of money has been wasted on trying to find wave energy converters that are viable. I'm currently at the Offshore Wind Expo in Glasgow, and you talk to loads of different wave energy companies, who do loads of testing, and there's so many that have failed in the past. Actually finding money to research into more is becoming a challenge. But hopefully one day, if someone can crack this one day, it'll be groundbreaking in my opinion. And the other one is floating solar, which is an emerging technology mainly for coastal areas or inland water areas. And this is particularly pertinent in places where you have like island countries like Indonesia. So there's a lot of research going into Indonesia because they have a lot of communities off the coast on little tiny islands that don't have any connection to the actual electricity grid. So the idea is that you have a sort of floating solar island just off the coast of smaller islands that can be connected to the grid and generate electricity for them, which is interesting. But that could work in the UK as well in inland water. So say if you have a lake or something like that. But again, to make that viable, it's probably a long way down the road. But these are just some of the types. But the main ones in the UK for us are definitely offshore winds. So the problem that we have is offshore renewable development often faces a number of complex but interconnected challenges, and this is basically where mathematics can play a key role. So I'll go through some of these challenges first, and I've picked out four main ones that I think are the most challenges. So political, we have first. So we often get policymakers make short-term decisions to garner a bit of political capital rather than taking the long-term decisions that can provide the regulatory and economic environment for offshore wind to thrive. Offshore renewable development to thrive. And an example of this was in the 2023, the fifth round of contracts for different scheme failed to secure any new offshore wind projects because the government didn't set the strike price too high, because obviously there was economic challenges after the pandemic. So they thought, yes, we can't afford this. But what that means is there's now a big hole in the development of offshore wind for the next 5 years. So that's a good example of how the political problems can cause further problems down the line. And obviously you get examples of where people just don't believe in climate change full stop. And obviously, like I was saying at the start, with the new president of the United States, doesn't believe it, doesn't really care, which is, well, he's democratically elected. So this is just part of the challenges that we have. And the next one, ecological. So I've just given an example here. So several studies suggest that offshore wind farms can produce excessive noise during their lifespan. So that's during construction, operation, decommission. So you've got to be mindful of the fact that that can affect the diversity of ecosystems around the areas where they operate. So there has to be a lot of research that looks into that as well to make sure we're not affecting the biodiversity there as well. Financial. So I've got a picture of the Bank of England here. So everything always comes down to money. It is the be all and end all of everything. So securing both state-funded and private sector investment is key. And I've just given some of the examples of where it costs money. So feasibility, planning, design, R&D, constructions, maintenance, insurance, legals, it all costs money, and that is the be all and end all. But in my opinion, the undisputed biggest challenge is engineering. So the marine environment is subject to harsh and potentially inconsistent wave conditions and wind conditions as well. So actually creating the technology that can survive in this environment and be viable is a major challenge as well. And yeah, it's these challenges that I'll refer back to throughout this talk, and how mathematics can play a role in tackling these challenges. So I'll start off with that engineering challenge, and the main thing that I think is important, and what my background is in, is mathematical modeling for design. So like I already said, the marine environment is subject to harsh and inconsistent wave conditions. So good long-term survivability is the key to any structure. If it can't survive, it's not going to be viable. And to get that survivability, we require a thorough and robust design process. followed by extensive numerical and experimental testing. And the quality of any design ensures that the structure is efficient as possible, both in a practical and financial sense. So going back to those challenges, making sure that the design is efficient and the structure is efficient will save you money in the long term, and then that will make your, say, political challenges easier as well, because you're more likely to get investment, etc. So this is very important. And just a quick example here. This is from my PhD. So this is just a little simple CFD simulation of an extreme wave. So a very it's actually called a focus wave. But basically an extreme wave event interacting with a fixed cylinder, which can just a simplified model of, say, a fixed wind turbine, and we can calculate the loads and stuff on the wind turbine and to see if it survives, essentially. So this is like the base. Before you can do anything, the mathematical modeling is key to designing any structure. CFD, computational fluid dynamics. So this is I'll go through two parts of mathematical modeling for design that I think are the most important. The first is CFD, and on the next slide I'll go through the finite element method. But CFD first. So this is my general area of expertise, and it's a vast subject. So I'll only go through it briefly. But basically, it's used for simulated fluid structure interaction, so wind and wave interaction with any structure. And some examples here: when you have the aerodynamic modeling of wind turbine rotors, calculating the thrust and power, predicting the hydrodynamic loads on structures due to wave structure interaction, like I showed you on the last slide, and also simulating the motions of structures in 6 degrees of freedom. So if you've got floating structures, to simulate the motion due to the waves, you have to use CFD models. Most CFD models are based on the Navier-Stokes equations. So these are key. The Navier-Stokes equations are the key mathematical principle that underlies all this. So, and I've wrote 3 properties of fluids that are important in the model there. So vorticity, viscosity, and turbulence. So those are very important in CFD modeling. And in general, your Navier-Stokes CFD models can be 1-phase, 2-phase, or multi-phase. So for 2-phase, you have air and water. And in general, they can be either mesh-based or mesh-free. So mesh-based is where you split your computational domain into small chunks and discretize it into small chunks and make like a computational mesh and solve the Navier-Stokes equations on each little chunk. Or you can have mesh-based, meshless methods like smooth particle hydrodynamics, which don't involve a mesh. And with that, you have a lot more scope for movements and stuff like that. But you can also have, sorry, just to go back a bit. So the Navier-Stokes equations are essential for modeling anything to do with vorticity, viscosity, and turbulence. But the problem with them is that they are very computationally expensive. So some Navier-Stokes simulations can take a very long time, and that, in the long run, sometimes isn't very efficient. So if you're trying to save money, if you're like an industrial company, for example, that is going to cost you a lot of money if you're doing loads of CFD simulations. So because of that, a lot of companies in industry use simplified methods like potential flow. And now these are very computationally efficient because they assume flow simplifications like the fluid being incompressible, inviscid, and irrotational. And they're useful for things like wave propagation, transformation, and wave-wave interaction. But you can't necessarily model wave structure interaction using these types of models. So you have a sort of dilemma here, and this is what my PhD was about. So my PhD involved developing an integrated model that coupled a potential flow model with a Navier-Stokes model in a bid to strike a balance between accuracy and efficiency for large-scale simulations. So with that, you could improve the efficiency without losing any accuracy. And in the long run, for your model, you'd save money financially. That was what my PhD was about, was to make this integrated model that can model waves far from a structure, but when the waves reach the structure, the small areas around it, it could model the Navier-Stokes equations and include these effects like volticity, viscosity, and turbulence, and simulate motions of the structure as well. So that's why CFD is important for design. So this is I've just got these off my PhD thesis, so I'm not going to go through all of this because it's quite a complex system of equations. But basically, these are Navier-Stokes equations I work with, and I specifically work with the volume of fluid method using the finite volume method. So I don't know if anyone who's an applied mathematician, you may have seen these before, but you have the Navier-Stokes equations. So we have, for an incompressible fluid, we have the incompressibility equation. Then you have a conservation of momentum equation where you have a temporal term, convection, diffusion, and source terms on the right that include the pressure. And I had a funky pressure term that was just easy for the simulations that I did, but has no actual physical meaning. But the key to this method is this transport equation for the quantity alpha, which we call the water volume fraction, that takes a value between 0 and 1. So if I show you this little simulation on the bottom right hand side here, this is just a 2D wave propagating from the left to right to this little T-shaped floating body structure that moves up and down and rotates. And the red bit represents alpha equals 1 is solely water. The blue bit represents alpha equals 0 is solely air. And then you have the interface in the middle, which takes a value between alpha between 0 and 1, and that represents the interface. So as you can see, when the wave travels and you get water on the structure, you get these sort of part of the flow where alpha is mostly 0 equals 1. It can't be defined as just solely water or solely air. And this transport equation for alpha basically models that, and that's called the volume of fluid method. And the key to this is that you take everything as a mixture of air and water using alpha. So for the velocity u, it's taken as a mixture of UW, which is water, then UA, which is air. And the same is for all the other constituents as well. So viscosity and the density as well. So that's just a quick little simulation. So if you look at the simulation there, that originally what this little T-shaped floating body is a simplified ship section. So it's supposed to simulate if water from a wave goes onto a ship deck, and you can basically see what the pressure is, how much it drags the ship down, and how it responds and stuff like that. So it's just a very simplified model, and that just shows like the sort of base that you can break everything down to. So yeah, that's CFD, which is one of the important keys. And the next thing we'll come on to, and the other part of mathematical modeling for design that I think is very important, is the finite element method. Now, this is important because we can calculate loads from CFD, so aerodynamic and hydrodynamic loads. But what the finite element method does is actually see how these translate onto the structures themselves. So it's key for determining things like materials and see whether different sort of materials would break under those loads. So structural analysis and fatigue assessments, this is what I was on about. So you can simulate how aerodynamic and hydrodynamic loads translate into forces and moments on a structure and its components. So I've just got a couple of examples here. So you have transient simulations can capture high intensity stresses that could compromise structural integrity. So if you have extreme wave impacts, you need to be able to know that the material that you've made your structure from can handle those high intensity stresses. And for that, you do a finite element simulation. And you can use techniques such as rainflow counting to predict accumulated fatigue damage over a structure's lifespan. You have these things called coupled aero-hydroelastic simulations, which can accurately capture interactions between forces and the structure. And I've got an example here. So if you have a rotor blade, the actual rotor will deform under aerodynamic loads, but in turn that will then alter the aerodynamic forces. So your power calculations and thrust calculations will be different. So to do this, you can run an FEM model to calculate that load. and then intrinsically feed that back into your CFD model because the forces will have changed. So that's a very advanced like system that you can create as well. And I've put at the bottom here, it's not actually limited to just the structures themselves. For example, you have soil structure interaction. So if you've got a fixed wind turbine fixed into the ground, you need to know, you can model how the bending moments and stuff with regards to the soil as well. So I don't think it's ever happened, but you could have a situation where the soil isn't strong enough to actually take the weight of a wind turbine under certain impacts, and it could fall over. Again, like I said, I don't think that's ever happened, but there is a possibility that could happen if you don't model it properly using techniques like FEM. Just a bit about the finite element method. So governing PDEs, so structures and components typically governed by linear and non-linear elasticity equations like 2D, 3D Navier-Stokes equations. The Galerkin method of weighted residual, so techniques like deriving a weak formulation, which allows easier handling of complex boundary conditions, where your boundary conditions can then be different types, like you can have a Newman condition, Dirichlet condition, or you can have mixed conditions and stuff like that as well, but it makes the actual computation easier. Spatial and temporal discretization, so like I said before, splitting the computational domain into different elements, and this is vital in my experience. So this doesn't just apply to FEM, but to CFD as well. What I found doing my PhD and subsequent work was, if you don't discretize your domain correctly when doing these numerical techniques, you can get serious problems. And this is a whole sort of domain in itself. Like, there's whole companies dedicated to meshing problems and stuff like that. Because as an example, if you have a rotating wind turbine, you have a boundary layer flow at the surface of the wind turbine, and modeling that boundary layer correctly is vital to the amount of power to actually model the power correctly. And if your mesh isn't good enough or isn't fine enough to calculate that boundary layer properly, then you're going to get seriously wrong results. So in my opinion, this spatial discretization is very important when doing any sort of numerical analysis. And like I said, yeah, there's entire companies that are dedicated to literally just meshing for CFD and FEM and things like that. Numerical solution method as well. So large algebraic systems, numerical integration, linear solvers, error estimation. There's loads that can go into this. I haven't got enough time in my talk to go through all of them. But yeah, there's a lot of other stuff with FEM as well. So there's any sort of vibrations, stuff like that. So when you have a structure, you need to make sure it's natural frequency. It doesn't cause a resonance with external forces as well. Otherwise, you'll get a catastrophic failure. So I don't know if anyone's ever heard of I think it was London Bridge, where the natural frequency of the bridge was getting close to the frequency of people walking across it, and it was actually moving. But yeah, stuff like that can cause catastrophic failure, and you can model that with the finite element method. Damping and things as well. So when you have a floating structure, like a floating offshore wind turbine, you get a lot of hydrodynamic damping, and you can model that with FEM as well. Yeah, so that's mathematical modeling for design. And I just want to go through a quick example. So this is a floating offshore wind turbine design from Equinor. And I just wanted to point out how CFD and FEM link together, and just how complex this whole system can become when using those two things. So first of all, on the actual structure itself, the floating base, yeah, you can do hydrodynamic load calculation from wave structure interaction, which you use CFD for. And then you can use those loads to calculate stresses, strains, displacements from the resulting load. Then on the blades, you can do aerodynamic modeling of rotor blades to calculate the thrust and power. And from that, you can do a structural analysis to calculate the blade deformation and fatigue to make sure it doesn't break over time. FEM on the stress on the tower as well, due to aerodynamic forces and wave-induced moments. So the tower as well, just the whole part of the wind turbine needs to be modelled. to make sure nothing breaks. CFD and modelling of the wake. So downstream wake modelling is essential for wind turbine layout, wind farm layouts, because the amount of energy lost in the wake is quite substantial. So when you're determining the layout of your wind farm, you can't necessarily just put two behind each other, because the one behind the other will mean that the efficiency of the second one won't be the same, because a lot of energy is lost in the wake. So that has to be considered when you're determining the layout as well. And that's why when you have wind farms, the distances between the turbines is usually quite large, like they can be up to 1 kilometre and over 1 kilometre in some cases. And that's because you want the wind to be unaffected by the wake by the time it gets to the second turbine. Otherwise, it won't be as efficient. Dynamic mooring line analysis, so the actual mooring lines as well, and the cables. From your CFD modelling of the base, you can work out the motion of the base and how that then affects the stresses and strains in the actual cables and the mooring. And I've got an arrow to the where it's fixed to the ground as well. So this will be the soil interaction that I was on about earlier. You can model that there as well. Potential flow modelling that I was on about a few slides ago, where you simplify the far wave field for the waves that propagate towards the actual structure itself. You can use potential flow modelling. The hydroaeroelastic simulations was all about. So, like I said before, you can use CFD to calculate the wind and wave forces in time, and then they're passed into the structural FEM solver at each time step. That then returns the motion and structural deformations, which will consequently influence the fluid domain for the next time step. So you get these two arrows here going back and forth into each other, and you have this intrinsic simulation, which is much more powerful than if you just did them both separately. And then rainfall cycling. So yeah, you use the CFD load histories to feed into structural FEM, generating stress time histories at critical hotspots like the welded joints and tail base. Now, I must confess, when I was doing this presentation, I researched rainfall counting, rainflow counting, and I couldn't make any head of it. So I've added it here if people want to look into it themselves afterwards, but I had no idea how it works. But it was interesting. It was interesting nonetheless, but I couldn't really get my head around it with the time I had. But it's important to calculate the fatigue over time. So that's mathematical modelling for design. And now on to the second thing that I think is very, very important. So like I said at the start, I work for NeuWave Technologies, who provide wave data for anyone with offshore assets, but focused on offshore renewable energy. And I'll go through why this is important as well. But first I'll go through what I actually mean by wind and wave data. So oceanography, there are wave action models for hindcast and forecast. So waves are a propagation of energy across the ocean, and wave action model is basically representing the irregularity. Takes a spectral representation of an irregular sea state, and that then describes how energy is distributed over frequencies and directions. So these are computational models where you can basically predict the different parameters to do with the spectral representation of a sea state. So to see what that means, I've got this graphic on the right hand side here. If anyone can, these are the Outer Hebrides. So we've got the Isle of Lewis, Harris, and the South and North Uist. And we've got this significant wave height parameter, which is one of the main parameters in ocean analysis, which basically gives an idea of what your average wave height will be in a certain sea state. So we can map over an area what the chances are of you to get these sort of different wave heights. And you get tidal knowledge. You can add tides and stuff into that as well, and meteorology. So that's where the wind comes in. The one thing I've mentioned here is hindcast and forecast. So there's different ways you can do this. So a hindcast is where you use past data to predict what it will be like today. So if you've got a wind speed of X today and a wind direction of Y, temperature of Z, you can look in the past and say that on this day we had a similar wind speed, a similar wind direction, etc., etc. So you can create an estimation and say that today, because in the past we had those and today we have those, maybe the wave parameters will be this today. That's what a hindcast is. You also have forecasts where you use forecast winds. So say if you get them from a Met Office and you've got a weather forecast for the next 5-7 days, you then use those to feed into a wave action model to create a forecast that way as well. So there's different ways you can do it, but they're all equally as important, but they're all important in their own different ways. And yeah, I've already talked about tidal here. You can add tides in as well, and meteorology in terms of the wind. And a more recent development is AI-driven models. So if you've got historical data, you can train, you can use machine learning algorithms to train these AI models to predict what the wave representation will be at some point in the future. And the reason why this is important, the first reason I've got here is resource assessment and site selection. So robust assessment ensures that developers choose locations that balance high resource availability with feasible installation, operation, and grid integration considerations. So you don't want to put a wind farm where you know there won't be sufficient wind, or where you know where the wave conditions are too harsh. So this is very important to make sure that, and you don't say if you have tides as well, you don't want to put your tidal stream turbines somewhere where the tidal currents aren't, where the tidal current isn't strong. So it's essential for that. And the next thing is construction, operation, and maintenance. So I've put two figures here. 1 in 12 days are falsely predicted as unsafe to operate, whereas 1 in 20 days are falsely predicted as safe to operate. And this causes delays in construction and exacerbates routine faults and major structural issues. So it costs money to send people out. And if you haven't got the right wave data and you decide not to send someone out to fix a wind turbine, then you're wasting time there and wasting money as well. And on the flip side, if you send someone out where it's unsafe because you haven't got accurate wave data, then that is also bad as well. And the one stat that always amazed me when I hear this is that offshore wind farm construction in the UK is delayed by 2 to 4 years on average. And a lot of that is down to just inaccurate forecasting, inaccurate wave data. Planning as well. There's a lot of planning, time waste on planning. And that's where this resource assessment and site selection can come in. Because we don't have accurate data, a lot of stuff gets delayed in planning because like the Crown Estate or etc. can't be sure that it'll be safe and things like that. So wave data, wind data, all this sort of stuff is key if you want to build a wind farm, operate a wind farm, or operate any other sort of renewable energy as well. Okay, so everything I've talked about so far in terms of mathematical modeling for design and wind and wave data, those are the things that I deem essential to the technological advancement of renewable energy, and those are the key parts, I think, especially for engineering challenges. But some of the lesser known areas that people don't necessarily think about are sometimes the most interesting, and I'll go through some of them now and link them back to the challenges that I was on about earlier. So the first is environmental impacts and sustainability. So if I go back to the ecological challenges that I had a few slides earlier, in terms of what I've got written here, so wave equations model the propagation of acoustics generated by pole driving during construction and the rotating during operation. You can only model this using PDEs and mathematics. So it's key to actually have an understanding of how the operation of offshore renewable energy affects the biodiversity around the areas in which they actually operate. And from that, you can use population dynamics and ecosystem models. So logistic growth models or reaction diffusion models can then actually track how fish, benthic organisms, or marine mammals move or change in density around the actual ORE sites. So maths is essential to modeling this sort of thing and seeing our effects on the marine environment due to offshore renewable energy. But not only that, so you can do life cycle assessments. So by using input-output analysis, so you can compute the total emissions across a supply chain by creating this linear system of economic sectors and their interdependencies, so raw material or composites for blades, and use this Leontief inverse matrix to calculate the total emissions. So this is a very clever tool, and then you can model the entire emissions across a supply chain and see where you're going wrong or where you need to reduce, etc. So yeah, environmental impact and sustainability. The whole point of renewables is for sustainability and to reduce environmental impacts. But there's things that go into it. It's not necessarily just the electricity generation, and these are just some of the ways where we can limit the environmental impact. Next, we have battery storage and grid generation. So this is very important. So in one of the first slides, I showed that I said that there's no point having loads of wind turbines if you can't then actually connect to the grid and then store more on overly windy days. So we had this problem with intermittency, where there was days where we were generating a lot of electricity from wind, then there was days that were less. And if you double the amount of wind turbines, you'll have, say, an excess of wind electricity, but there's no way to store it. So battery storage is very important, because I always hear politicians, commentators say that when the wind doesn't always blow and the sun doesn't always shine. That's not necessarily the case. The wind is always blowing somewhere. You just A, have to put the wind turbines in the right place, and B, you have to have enough storage capacity where on the bad days you can use the capacity generated on the good days to stop the intermittency. So it's a problem that can always be solved, but sometimes people don't actually want to put the effort in to solve it. But this is where mass can play a crucial role. So for battery storage and grid generation is very important. And I've got some examples here of how it's important. So electrochemical and thermal models. So ODs and PDs model internal chemical reactions like lithium ion transport, heat generation and dissipation. Power flow analysis. So integrating offshore renewables with onshore grids involves solving large sets of nonlinear algebraic equations. And then you can use methods such as Newton-Raphson to find voltages, currents, power flows, ensure that there's feasibility and voltage stability. And for me, when I was researching this, it was quite nice to hear about Newton-Raphson having a real-world application, because I remember in your first year of A-level, you get taught Newton-Raphson on how to solve ODEs. And since then, I'd never actually heard of it having a practical application. So when I was writing this and doing this presentation, it was nice for me to hear. It was quite nostalgic to hear that it's actually got a real world use. So things to teach you in school are always important. Probabilistic forecasting. So integrating storage optimally with variable wind and solar requires accurate forecasts of generation, demand, and market prices. So this goes back to the intermittency again. If you can create these models where when there's less demand, so electricity is generally cheaper, and you can automatically detect that and start storing then without taking too much electricity away from the grid, then you can save that for later and it's cheaper. So having these forecasts of when's the best time to do that is quite important. And this already happens on a smaller scale. So companies like Octopus have these smart tariffs where at night, where energy is generally cheaper, you can connect it to your electric vehicles and things like that and use cheap energy to charge those. And there's companies like Tesla, I think some of Tesla cars, but also different products can act as battery storage for your house. So you can store cheap electricity that you've built up at night and then release it in the day if you need it, just to make your generation in the day cheaper. And that's the sort of thing that probabilistic forecasting builds into. So all of this is quite clever stuff that could make electricity generation and distribution cheaper. Optimization. So layout optimization. So I said on my CFD slide that the layout depends a lot on the wake dynamics. So there's in the unsteady wake of a wind turbine, there's power loss. So the way that you position your wind turbines is essential. And you can then use mathematical algorithms like genetic or gradient based to position your turbines for max output. So what you're doing here is optimizing the minimum loss of power due to the wake. So this just links back to the CFD earlier. You can then use this to optimize your wind turbine layout. Cost optimization, so life cycle cost analysis for materials, maintenance, and production. So everything costs money. If you can minimize and optimize your costs, that's always a benefit. Supply chain and logistics. Integer linear program to optimize transportation and installation schedules. So this is stuff that I don't think anyone usually thinks about. But if you're building a wind farm and you've got your wave data has told you that it's okay to build today, if you've got your schedules wrong and your transportation wrong and your lorries that are actually bringing your materials to the coast for you to build are like 2 days behind, you're wasting time and you're wasting money there as well. So getting this sort of stuff right is also essential. And like I said, it's stuff that no one really thinks about. The big things that people think about are the actual technology themselves, but these sort of small things that involve people are important as well. And mathematical techniques like integer and linear programming and making models of this can help to optimize that as well. So that's all important. Reliability and risk. So these are essential for the financial and political challenges. So probability is very important. So at NeuWave Technologies, we use statistical techniques to find extreme values. So you need to know the probability of the harshest conditions over the lifetime of a renewable asset. So you can get a better understanding of how long it will last, etc., and the risks involved. And with that, you're only if you've got a better idea of the risk involved, you're more likely to get investment and finance. So probability and stochastic analysis evaluates the likelihood of extreme events and failures by capturing a full range of conditions over a structure's lifetime. This is essential stuff. And Monte Carlo simulations. So these are important in many fields, particularly in financial maths and stock markets and stuff like that. But they're important here as well. So you can use them to handle the uncertainty in input parameters. So when you've got variable weather conditions and uncertain sea states, you can create these ensemble weather and wave forecasts, which are a form of Monte Carlo that can give you a range of potential forecast outcomes. And then once you've got that information, you can make a more informed decision and you can assess the risk yourself rather than just having to rely on intuition. And then risk-based decision making in general, like I said, for making more effective decisions as well. You can inform design choices, insurance, investor confidence. So that just links back in to the risk aspect, because what people don't generally think about as well, but what's quite interesting is actually the insurance on wind farms or wind turbines or wave energy converters specifically are quite high. So wave energy is a very tough nut to crack, like I was saying at the start of this presentation. So actually insuring your prototypes costs a lot of money because there's a lot of risk involved. So actually finding the investment or finding a company that will insure it, it can be quite a challenge. So if you can do anything with probability to de-risk that and bring down these premiums, then it's beneficial. And then lastly, my last slide is on the future. Machine learning, AI, and digital twins. Now, I've said the future, but I think it's very much the now as well. So starting off with AI-driven modeling and forecasting, so with wave data. So you can leverage machine learning algorithms to predict sea state variables more accurately and efficiently than traditional computational methods. So that's what we're going to start doing at NeuWave at some point in the near future, is rather than using wave action models to simulate this over large areas, you can use artificial intelligence and machine learning to use your past data, your hindcast data, to predict what will be in the future a lot more efficiently, so you don't have to run simulations with loads of equations. You can just leverage machine learning to do that instead. Adaptive control, so reinforcement learning to optimize turbine pitch and yaw calibration, more inline tension, and you can do all that in real time, which will boost power output and minimize stress. So I've got an image on the right hand side here, which is from a Danish company that I'll reference on the next on the last slide, of an onshore wind turbine, where you can see that they've sent up a UAV, a drone, took images of the wind turbine, and then they feed that into an image detection tool. Sorry, I've started talking about the image detection. That's for predictive analytics and operation and maintenance. But I'll carry on with that. So yeah, so they feed it into an AI image detection tool, and that'll give you the probability of whether it needs fixing. So then you don't waste time and money on actual maintenance if it's not necessary. So for an offshore wind turbine, you don't need to send someone out to go and fix it and send someone up if it doesn't need fixing. You can just fly a drone out from the coast, however many kilometers it is, check, use this AI image detection tool, and then say either yes or no. That saves you a lot of money. So like I said, yeah, that's for predictive analytics for operations and maintenance. So you can also use sensor data like vibrations and temperatures, and then this guides proactive maintenance for critical components. But going back to the adaptive control that I was saying, so if the wind direction and speed changes, and you've got a wind turbine, the control mechanism, if it's AI driven, can automatically change the settings, so the pitch, the gearbox, etc., rather than having to do it manually. So it can be a lot quicker, because what a lot of people don't realize with wind turbines, the blades are essentially aerofoils, so they're the same as airplane blades. So the angle of attack at which the wind actually strikes the blade is critical to the amount of lift force that's generated, and in turn the power that's generated as well. So if you can do that automatically, you can reduce the amount of downtime without having to check the wind, etc. First, you can do it automatically, and then you can boost the power output. And yeah, so these are some of the ways in which AI machine learning, particularly for offshore wind turbines I've talked about, can boost efficiency. And the last thing is digital twins. So a digital twin is a virtual replica of a physical structure or system that is continually updated with real-time data from the structure's operations. So the twin mirrors responses from simulations and then synchronizes them with actual empirical measurements. So you have an actual offshore asset, say an offshore wind turbine, and you can feed those results into your simulations and create this thing called a digital twin. And then what that does is then contribute to better predictive maintenance by spotting faults early, which improves the reliability and reduces downtime. But what it also does is you can run what-if scenarios of extreme events on the digital twin without actually risking the real structure. So on Friday, we've got a red weather warning for wind across the UK. So you can feed those scenarios into the digital twin, and then you know whether you need to turn your turbine off or if the winds will be too dangerous for it. So it can have real life save your structures in real life. So rather than having them on when it's dangerous, you can turn them off, or you can just change the settings. So if the wind on Friday reduces, you can run a lot of different scenarios and find the optimal settings for it without actually having to manually change it on the turbine itself. And on the bottom right, I've got a picture of the marine simulator at the University of Plymouth. Now, I don't think this is strictly a digital twin, but it's a similar sort of thing, and I wanted to add it on because it sort of amazed me when I went there. It's basically a boat simulator where you walk in, and they use empirical data for the waves and stuff like that. You can model loads of different things, like you can model the towing of a wind turbine, a floating offshore wind turbine, to its position using the boat, and you can see how that affects the boat. Cranes as well, so you can tow cranes into their positions and see whether they topple or not and things like that. And it's I found it a really cool thing and a really cool place to visit. And in essence, it works the same as a digital twin, but you're not actually modeling the offshore asset. You're just simulating the actual boat that takes it there instead. And yeah, it was a funny place because it was, even though you're not moving, it still makes you feel seasick because the screens are moving. The image on the screen is moving, even though you're not moving. You still get the feeling of seasickness. So yeah, it was a really cool place to go to. And that's everything. So I've got some of the references, the things that I've referenced in the presentation here, but I hope I've given everyone a decent understanding of how mathematics plays a part, first of all, has played a part in the technological advancement of offshore renewable energy, but how it will always will continue to play a part as well. So I didn't want to go through loads of equations and stuff in this presentation. I didn't want to bore people with that, but I wanted to give people an idea of just how interesting it can be and some of the lesser known areas where it can have a big difference and yeah, help us on the route to net zero with renewable energy. Thank you.
Thank you very much, Ranjodh.